So I'm going to talk this morning about optimizing IP networks for video acquisition. As we all know, in the station business, in the television business, everyone's clamoring for more content, obviously at low cost. Stations these days differentiate themselves from their competitors by the quality of their content, what they aggregate, what they're able to bring to their viewers. This is particularly true when it comes to news and live sports coverage, where live is the key differentiator between the content. Stations have been realizing, at the same time, stations have been realizing the many advantages in moving to IP-based workflows. And, oops, excuse me. Is there a mouse on here too? Yeah. Oh, okay, got it. Yeah. Thank you. Sorry. Stations have been moving to, at the same time, to IP-based workflows, which bring their own challenges from the traditional SDI-based workflow that we're all accustomed to. Chief among those challenges is how do we reliably acquire and deliver HD broadcast quality live video from any point in the field, in the studio, to our viewers. Solution obviously is to work within that IP-based infrastructure. Stations today working in IP have the option to aggregate multiple different transmission methods and bring adaptive video coding rates into play to deliver high quality or HD quality content to their viewers. One of those methods to acquire content obviously is mobile cellular. With the preponderance of 4G and LTE networks being built out domestically and throughout the world, greater and greater amounts of bandwidth are being made available for station employees, for news gathering employees, to acquire and deliver that content back to the studio, and then for studios in turn to redistribute that content out to their viewers. However, just having bandwidth isn't enough in many cases to get those strong, high-quality pictures, and this is where some of the technologies that I'm going to discuss today come into play. Chief amongst those is packet loss management, error correction, and variable bitrate encoding. So obviously we have a number of transmission mediums that we can use in the IP-based world. There's IP over satellite, IP over microwave, and obviously cellular. All of these types of connection mediums have their own hits and misses. Satellite, we all know, can be very expensive. In many cases, satellite coverage must be prearranged or pre-coordinated, and weather can affect satellite coverage just like it can some of the other methods. Microwave, limited coverage. If you're outside of your station's microwave field, you're probably not going to get a signal. Can be a high capital expense, obviously getting a microwave network up and running, and it does generally require very skilled operators. Cellular, of course, has its weaknesses. Limited coverage in some markets. In many cases, there is not pre-existing cellular communications equipment in a station workflow, so this again can require new hardware and can be a capital expense. The ideal coverage would be something that can aggregate all of these networks together to give us one solution that can play off all of the strengths of the individual transmission mediums. So, over IP networks, I'm going to stop here for a second and talk about some technical terms for IP networks, just so we're all on the same page. There are a number of factors that can affect perceived speed of IP network transmission. First amongst those is bandwidth. Bandwidth obviously is the maximum bit rate that you can transmit over a given connection. Then there's throughput. Throughput is the actual rate that you're going to see over a given connection. So you can think of that as the throughput being limited by the theoretical maximum that bandwidth provides. Latency in the network world refers to a delay between sending and receiving, generally packets in the traditional IP world. Jitter is variation between the time a signal is sent and the time a signal is received. If any of you have ever used a Skype call, I'm sure you're very aware of what jitter sounds like when you're receiving packets at random times. And then finally, error rate. Error is the number of packets that are missed, basically, at the receiving end. So all of these taken together will give us perceived speed of a given network connection. And this is the same over any given IP network, whether that's a cellular IP network, satellite, microwave, or any other IP network. So what do we do with these technologies, and how do we bring some solutions to bear to give us optimized quality over IP networks? Chief amongst those is the bit rate that we can achieve, and that's going to be the #1 driver in the picture quality that we're getting on the receiving end. Traditional encoding has been constant bit rate encoding. In the cellular IP world, generally we're working with variable bitrate encoding. This gives us a little bit of a higher bit rate when encoding complex video streams, better quality when compared to CBR. With TVU, we've actually brought into bear what technology we call smart VBR, that in addition to moving the allowing for the higher bit rates when encoding, gives us the ability to change resolution and frame rate, compensate for fluctuating networks that we see perhaps when driving from point to point. And with H.264 encoding, which is generally what we see in the cellular aggregates, we want to shoot for 8+ megabits for HD quality and 4+ megabits for SD quality. These, of course, are targets. Not all the times these can these be achieved, but this is a good number for broadcast quality HD and broadcast quality SD content aggregation. Some of you may have heard of link aggregation or bonding. These are actually separate technologies. Link aggregation is the ability to put multiple IP connections together. Bonding actually ties them together. So one reason link aggregation is preferred over bonding when looking at IP contribution is that bonding creates a single channel. This is great when you have a fixed network. So wired networks, typical T1s, T3 connections, where we have fixed data rates. Bonding can really take advantage of those fixed data rates, give you improved performance and reliability because of redundancy. Unfortunately, bonding falls apart a bit when we have varying data rates that we find in everyday cellular and mobile IP networks. Because of that single channel creation in a bonded network, your fluctuating networks can actually bring down the overall speed or the overall throughput of a bonded connection, because it's limited by the lowest common denominator in that bonding connection. Right? As we have those fluctuations in bandwidth, in packet loss, in latency, and other performance metrics, that lowest common bond can actually bring down the overall network performance. So this is where we focus on link aggregation as opposed to bonding. In addition to link aggregation, we have to worry about managing packet loss. So packet loss, obviously, hopefully you can see this over the projector. Packet loss can result in a degraded picture quality. The picture on the left represents a signal with some packet loss. The picture on your right represents a high quality picture with no packet loss. Packet loss can be managed via a number of methods. Retransmission has been the historical method to manage packet loss. Obviously, retransmission means the receiving node asking the sending node to retransmit packets. Right? While this works fine in a store and forward type of situation, For live video, this results in a lower aggregate throughput, and you have to then settle for lower picture quality or higher latency. One of the chief ways to manage forward packet loss without giving up on that picture quality or increasing the latency of the signal is by bringing in some forward error correction technologies. Looks like our picture's off a bit there. Forward error correction is chiefly designed when using video over IP for correcting for packet loss. Right? The FEC, or forward error correction, is basically a process for stuffing additional packets of encoded material into a data stream so that on the receiving end they can be decoded and give you excellent picture quality without having to result in retransmission. Right. We can see here that we have source video, an encoder, and we have extra packets in the encoded video section. Even with some packet loss, the decoded video results in a complete picture quality. In addition to having forward error correction, we can look at technologies like inverse statistical multiplexing or inverse stat mux. Traditional muxing generally involves combining multiple streams over a single high bitrate data stream. Inverse stat mux is basically the opposite of that, and that's where a high bitrate data stream can be split over multiple IP networks and recombined at the receiving end. So this breaks packets into, or breaks video streams into many small packets. The packets are then transmitted via each link independent of the performance of the other links. And again, at the receiving end, we rely on the receiver to put all those packets together. All of this is done primarily over IP networks, IP layer 4 networks. So this is basically handled by the encoder and the receiver in direct communication. This can be TCP or UDP. And then error correction, as I mentioned, is done at the receiving end. In addition to FEC and traditional inverse stat mux, TVU has implemented what we call inverse stat mux plus, which is an improvement on traditional FEC algorithms. Right? Basically, we're stuffing even more packets down a wire and relying on the FEC and the stat mux to give us ultimate picture quality at the receiving end. Right? The algorithm that we're relying on for that FEC is then accomplishing basically ideal throughput on a given connection. We're managing to stuff as many packets down a given pipe and then aggregate them at the receiving end. The end results to some of these technologies is that you are then able to aggregate different transmission networks on a single connection. Right? This can be satellite, microwave, Ethernet, cellular. And all of these are discrete IP networks that then can be aggregated, again, not bonded, over a single connection and put back together by the receiver. You want to keep in mind that your solution should be able to dynamically add and remove any of these connections. Right? If we're in a fixed location, the connections generally don't alter too much or fluctuate too much. But in a dynamic or moving situation, if I'm shooting video from a moving vehicle, I want to be able to dynamically deal with fluctuations in the given networks. By aggregating, we can achieve sub-second latency, again, even from a moving vehicle. And we can see real-world throughput of 10 plus megabits a second with some of these technologies over cellular-only communications. Right? Without things like FEC, without things like inverse stat mux, we're relying on the upload speed of cellular networks. And as we all know, cellular networks today are optimized for download speed. So bringing FEC in, bringing inverse stat mux in, being able to aggregate connections is where you're going to see the real-world performance of HD quality live video acquisition in that sub-second latency range. In addition to that, obviously, there's high success rate, right? Very important in bringing video in from the field, because if we can't get a connection over satellite, we have to rely on other sources. If we can't get it over microwave, we have to rely on other sources. So the ability to aggregate all of these networks yields a high success rate, a confidence in your ability to aggregate that live video, no matter what the given IP situation looks like. In addition to being able to route IP video from the field, we also have workflows that we need to enable for routing IP video from studio to studio, from head-end to studio, to our transmitters. Right? The same technologies that we can apply to acquiring live video content from the field can be applied to video switching, routing, and distribution from fixed points. Right? So again, FEC, inverse stat mux, and other tools to manage packet loss and speed delivery can be brought into routing video from point to point. With TVU, we have a web-based grid solution that lets us accept SDI video sources as well as IP video sources. You have to keep in mind that you may need to consider frame-accurate switching between IP video sources. And then also keep in mind how you're going to fail over any of these solutions that you may be considering from point to point in case of network outages or building environmental outages. There are also factors like scheduling. Right, with the ability to bring in video feeds from many different sources, we need to think about how we're going to push those videos out. Obviously, there's interaction between IP and SDI-based infrastructure, but in the IP world, we can also keep and push video out to over-the-top providers, CDNs, and other sources where the video stays in IP. And this is where scheduling solutions come into play with that IP video workflow. You want to be able to, if possible, feed all of the viewers in the non-traditional content consumption side, where the video is going to go to the handhelds and the mobile devices and such that you were talking about earlier. So as viewers continue to expand what they consume, right, local content is obviously still of the most importance to them, and especially to us in this group. As I'm sure you're all aware, and as I'm sure everyone has seen with the metrics, even as younger viewers are consuming less traditional over-the-air broadcast, they are consuming the same amount of content, if not more increasing content. So as you consider IP workflows and IP solutions into your existing workflows, keep in mind that you want solutions that are going to deliver content out to those edge cases, to those younger viewers, to those tablet devices, to those mobile devices. And that's where keeping the workflow in an IP, keeping your video in an IP workflow really comes into play. Broadcasters obviously are in a state of flux with the transition from SDI to IP that everyone knows is coming. But we do see that, that these technologies, as they come into bear, are more cost-effective, in many cases are simpler to operate, and they ultimately give us a lot more flexibility in providing for these over-the-top and IP-based content distribution methods. So I know we're a little short on time. I'll hand off back to you, Bruce.